When I look in this picture, it was voluntary muscles that flexed this shoulder and flexed this elbow and held up this piece of plastic. All of these voluntary muscles put this arm where it needed to be so that he could blow these bubbles. Our skeletal muscles have a lot of nerve supply, and a term for that is innervation. Nerves innervate muscles. Here in this picture, we're seeing the spinal cord, one nerve going to several muscle cells. And so this would be one motor unit. A motor unit is all of the muscle cells that are controlled by one motor neuron. Remember, motor tells us it's going to cause movement. To plant a seed for this section, imagine this is one power strip, 4 sets of lights plugged into it. This would be like the innervation, controlling these voluntary lights. You can voluntarily turn them on or turn them off. But the idea is this motor unit is going to work together. If this power strip is turned off, all of these get turned off. If this power strip is turned on, all of these get turned on. There's no way that these lights could be on at the same time these lights are off. They work like a unit. The same thing. They said that there was thousands of these muscle fibers in some cells. And each muscle has lots of motor units. Some of the muscle cells that are controlled by one specific nerve. This is the last block of 223 where we're actually going to do some dissection of sheep brains and be able to see some spinal cord. But these motor neurons come from the spinal cord or maybe from the brain and go to the muscle fibers. Specifically, it's a part of the motor neuron called the axon. Axons carry information towards the muscle cells. These motor units can really vary. Some are really small, like the precise holding something between your thumb and your first finger and putting a key into a lock. Those are really detailed movements, precise control. So those are small motor units. Others are large motor units. If you were going to jump as high as you can, you would fire off the large motor units and the big muscles of your quads, your thigh muscles, and your back muscles. And that picture we were seeing of a motor unit is really a little bit deceptive. We said that there might be 1,000 of these muscle cells, but that motor unit is going to be spread out, and all of the muscle cells aren't going to be together. Like it's going to control that one, and that one, and that one. And then a different motor unit comes in and controls that one, and maybe that one, right? Lots of different motor units are going to the same muscle. It's not just a one little clustered part, it's spread out. Another important portion, here's the axon of the nerve going down into these muscle cells. And we want to talk about the neuromuscular junction. A junction is where things meet. So here they're showing one, but there's actually like 3 neuromuscular junctions in this illustration. That's where that motor neuron actually innervates or actually controls the muscle. Usually it's kind of right in the middle of the muscle, but it can vary a little bit. There's 3 key parts to a neuromuscular junction. Make sure by the time we finish this, you can identify the synaptic knob. That synaptic knob is part of the nerve. Right there is one synaptic knob. And the next thing is the cleft. The synaptic cleft, that's actually a space. And so like I could fill in all of this space here is the synaptic cleft. And then the third part is the motor end plate. And the motor end plate is the portion on the muscle itself. What am I describing? The 3 parts of a neuromuscular junction, where a nerve meets a muscle. First, we have a synaptic knob. That synaptic knob has a little space called the synaptic cleft. And on the other side of that, on the muscle itself, is the motor end plate. The synaptic knob, remember that's that far end of the axon right at the end of it? Inside it has vesicles. And when I think of a vesicle, I think of like a wine bottle. Pretend I drew a better wine bottle than that. I think of like a wine bottle, or maybe if you've ever seen like a pirate movie, how they have the clay pots, and those are what they kept their liquids in. So a vesicle, it's like a little pouch. And lots of different structures can be stored in different vesicles. Here, where we're dealing with voluntary skeletal muscle, we're going to have a specific neurotransmitter called acetylcholine, ACH. ACH is inside these synaptic vesicles. That synaptic knob, besides the vesicles, it also has some pumps so that it can move calcium to really keep that gradient where it's supposed to be. It also has voltage-gated calcium channels. When electricity goes through there, it really opens up and lets calcium flow into the cell. I'm going to skip down. When we were looking at the picture, the next thing we saw was the space, the synaptic cleft. A cleft is a space. Maybe you know somebody with a cleft chin and it has a little space between there. A lot of cartoon characters, they draw those in. So the synaptic cleft is the space. It separates that synaptic knob from the muscle's motor end plate. There's an enzyme that stays in the synaptic cleft, sometimes just called ACH ACE, but technically acetylcholine esterase, and that's what breaks down acetylcholine after it's been released. Remember, acetylcholine was stored inside the vesicles. When electricity comes down, that acetylcholine is released from the vesicle, crosses across the synaptic cleft, and goes to the motor end plate. The motor end plate is part of the sarcolemma, or the muscle cell, and that's where the acetylcholine receptors are. So it receives the acetylcholine. This acetylcholine basically says, hey, it's time to do some work. Let some of those ions flow through. And so sodium goes into the cell and potassium goes out of the cell. Let's put this together in a picture. The nerve, the motor neuron was coming through here, and at the end of the axon it swelled up. And it formed that synaptic knob, that big structure. Inside the synaptic knob was a vesicle, a little pouch. And inside that pouch is acetylcholine. Acetylcholine is the neurotransmitter. It says, hey, this nerve is firing off, time for the muscle to do some work. When it gets excited, it's going to let more stuff come in and go out. And that acetylcholine goes from the vesicle, and it's going to cross over this space here. This space is the synaptic cleft. Here I have acetylcholine going into the cleft. And eventually that acetylcholine is going to find receptors on this other side here. This is where the motor end plate is. All of this causes a lot of chemical reactions as well, as sodium and potassium go through some changes to change the charge. So all of this comes down to electrochemical energy. We used that term way back in chapter 3, I believe. Electro because we're dealing with electrical impulses, and chemical because these chemicals have charge. First, we're going to look at a muscle when it's at rest. It has a resting membrane potential. Way back in the energy chapter, we talked about how like a ball or a boulder sitting on top of a hill has potential energy. It's just at rest. It's just sitting there. But it wouldn't be hard to get it going, and then it's going to use a lot of kinetic energy as it moves down the hill. Potential energy at rest, resting membrane potential. The difference between inside the membrane and outside the membrane. Key ideas for our notes. Inside the cell is negative compared to the outside. Right here they're showing you, right here's the outside with the little positive sign, and notice there's negatives on the inside. Inside is negative. Specifically about negative 90 millivolts. And that's how it is when most of the time you're just sitting around and your muscles are not being used. The inside of the cell is about negative 90 millivolts compared to the outside of the cell. And the way that's maintained is a little bit of sodium and potassium gets pushed in or out just enough to, like it drops to 89, a little bit brings it back to 90. It goes to 91. So all of this resting membrane is with things leaking in and out. Not much is going on. The membrane potential doesn't change much at rest. More details about this. When we start to get excited, when this axon, when this nerve fires off and the synaptic cleft takes these vesicles and it's going to release all this acetylcholine, release of neurotransmitter acetylcholine from the synaptic vesicle. It's going to exit here. Remember, it's actually got to cross through the cleft before it gets in there. But this acetylcholine causes things to get excited. So we start to make what's called action potentials. And these action potentials carry on into the cell using these T tubules. Remember, they were the transverse ones that went from the surface down deep into the myofibrils. This started because of acetylcholine. That was the neurotransmitter. It made an action potential. We're going to define better in the next slide. All of this causes the muscle to contract. When muscles contract, things go toward that midline. Thin moves in. Sarcomeres are shortened and the skeletal muscle is doing some work. It's contracting. All of this is going on because I want to move my arm or because I want to do some voluntary movement. Up in the nerve, in that synaptic knob, calcium comes in. Electricity started either in my brain or spinal cord. That nerve signal went all the way down the axon. It eventually got the synaptic knob, and it opens up voltage gated. Voltage because nerves carry electricity. So calcium goes into the synaptic knob. Calcium actually kind of like cracks the seal, like popping a champagne bottle, and opens up those synaptic vesicles. Remember, those synaptic vesicles had acetylcholine. And they use that process we learned about with the cells, exocytosis, stuff exiting the cell. Exo for exit, cyte for cell. So what are we saying? When the nerve gets excited, calcium goes into the synaptic knob. It kind of pops the champagne bottle for these vesicles, and acetylcholine is released from the synaptic vesicle. Here's the nerve, here's the synaptic knob. The nerve's been fired, gets real excited, so calcium goes into the synaptic knob. Calcium kind of interacts with these vesicles, popping the champagne bottles. It releases the acetylcholine. It's going to cross over and go to the motor end plate. It passes through the synaptic cleft and interacts over here. As complicated as this is, unfortunately, it doesn't always work. A pathology to be aware of is called myasthenia gravis. And my points you to a muscle problem. And gravis is a Latin term for gravid, or being very, very serious. This is an autoimmune, so the body attacks itself, most commonly in women, but men can get this as well. Anyone can get this. What happens is the body starts to attack those acetylcholine receptors. And that means the muscles can't be stimulated as well. And so people just, not only do they get tired, they really lose their strength, muscle weakness. The big idea is I'm not going to be able to walk, not going to be able to carry things as far. But often it first starts off in the face. I have trouble, or the patient would have trouble, like laughing a long time. My face wouldn't have the stamina to laugh during a 2-hour movie. My face would get tired. Unfortunately, this progresses to not only limb weakness, in severe problems, I'm going to have difficulty swallowing and breathing. Gravis, it's very, very serious. Having to do with my muscles. Back to our complex idea that when a nerve gets stimulated, it releases acetylcholine. This acetylcholine crosses over to the motor end plate. We're going to define on the next slide the end plate potential. The difference between the charge on the outside and inside. The end plate potential is only specifically right here. And so think about like a domino effect. The end plate potential is right at the end plate. And then it's called an action potential as it takes action and moves down the sarcolemma. And technically it's still an action potential as it goes down the T-tubule. All of this is getting more and more electrical chemical charges so that calcium come in and calcium can do its work. Let's try to use our words for here as well. All right, we know that the end plate potential, that was only right there by the synapse. And it's specifically receiving that acetylcholine, so we have acetylcholine receptors. As soon as acetylcholine is there, sodium comes into the cell. Mostly sodium's coming in. You do lose a little bit of potassium. It just keeps the cell from basically doing too much work too fast. But big idea, sodium comes in, brings this big positive charge in here. So now my inside is less negative, or we could say closer to positive. But that end plate potential is very local. It's only right there by the synaptic knob. The end plate potential like gathers up this energy and it hands it off to the thing right next to it. As soon as we start passing down away from the synaptic knob, we're going along that sarcolemma, and technically, remember, it dove down into the T-tubules. Now we're not an end plate potential, we're an action potential. An action potential, it looks like a wave, but think about like when you're putting a sheet, when you're doing a sheet on the bed, and how if I take a sheet, that sheet, I would put a little wave in like that, but then in the middle, that sheet kind of looks like that. And then at the end, it kind of looks like that, right? It's just, you just flipped it up through there. It's just passing it down through there. All of this is because sodium is moving at that specific area. As soon as my inside is changing voltage, the term for that is depolarizing. I'm getting less negative. I started off probably somewhere around -90. For a split moment, I go all the way to +30. I depolarize. Go from the bottom to the top, and then I've got to go back down again. So it's a chain reaction, passing straight down this sarcolemma, going down the line. A term for that is propagating. Think about if you've ever seen like a sporting event, a Vegas Knights game, right? And there's the hockey ice, and all the fans start doing the wave, right? This person stands up, goes, hey, and then this person, hey, right? And it goes all the way around. A term for that is propagating. All the fans are doing the exact same thing, but they're not doing it at the same time, right? This person is setting down while the wave's over here. So it's propagated around the rink or the arena. And here we've propagated this signal as it's gone down the sarcolemma. It's continued on. After that wave passes, we depolarize, and then we return to where we started. We repolarize. To put it in my wave example, I'm depolarized when I'm standing up and going, hey, but then as soon as I do that, I set back down. So now I have repolarized. I know this is complicated. We'll put it together with a couple of pictures. Again, most importantly, all of this is about exciting a voluntary muscle. I'm releasing that neurotransmitter called acetylcholine, and that acetylcholine has to cross from the synaptic knob here to the muscle at the end plate. Exactly here, each one of these little pluses and minus is doing an end plate potential. All of this is like, hey, here's a +1, and hey, here's a -2, and here's a +2. All of this, but it's only right here is the end plate potential. Then we're going to pass it this way. As soon as we get past the synaptic knob, now it's no longer end plate potential, but action potential. Each one of these is taking some action, doing a little work here, but then it's going to reset, and the work's going to go to here. Work's going to go to here. Here's that propagation. If we look at it on a graph, this is showing us time and the charge. Remember, the inside of the cell is typically about -90. In the middle of that doing the wave, as we depolarize, we actually become more and more positive. We actually cross over zero. So we start at -90, we go all the way to 30, but we're just there for a second, and we dive back down. So to put some terms with this, the first thing that happened is we're at rest. We have no stimulus here. So when we rest, our resting membrane potential is typically about -90 millivolts. Big idea. Threshold is what it takes to get a response. Think about like Family Guy when Stewie's like, mom, 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 mommy, 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 hey mom, right? Mom hits her threshold. She's like, Stewie, right? Threshold is what it takes to get a response. The threshold is not -90. Typically, the threshold's a little bit closer to 0. So the threshold tends to be about -65. What's that mean? Here is we're able to ignore. Hey, Van. I ignored that. Van. Boom, I hit my threshold. As soon as I hit my threshold, that's when this sharp depolarization happens. Quickly, it goes from -65 all the way up to +30 millivolts. Look at that big jump. But then we have to repolarize. We just fire it off, right? Just like when somebody has had enough and they snap, usually they need a little time to relax. So they have to repolarize. Planting a seed, repolarization takes longer than depolarization, right? How long does it take to get mad? Boom, you snap. How long does it take to calm down? For the next several minutes, you're like, all of this has to do with the different ions getting back to where they're supposed to be. But repolarization will bring me back down closer to that -90 millivolts where I started. All of this is happening down that sarcolemma. Remember we showed that line how it just happens here, then it happens here, then it happens here, all the way down the sarcolemma. And it also turns and goes deep into the muscle in those T tubules. Again, the big idea, we're involving calcium to get some energy going. But here's where once I get down deep into the muscle, remember that sarcoplasmic reticulum actually stored some calcium. It said, I'm going to have this so that when Van needs it, I've already got calcium right here. And this calcium can trigger the contraction. What we're talking about is tying in the nervous impulse that started way up there in the nerve. Electricity came down. Then it became chemical impulse once the neurotransmitter was released. And then other ions like calcium and sodium got involved. But it's the calcium that actually triggers the muscle to contract. That action potential started way up here. Remember, to the left of this was the end plate potential right by the synapse. Now we're action potential. All of this little bitty charges get passed all the way to here and dive down into the T-tubule so that they can get to where the sarcoplasma had stored calcium. And calcium is now released from the sarcoplasmic reticulum. Remember, to tie this in, right here are these muscle cells, those filaments that are going to contract. And in order to contract, they got to have calcium. Hang in there, everybody. I'll see you in part 3.